Okay, so what we're going to do in this video is we're going to look at some exponential growth and decay. So the idea behind exponential growth and decay is that most natural phenomena grow in a way or decay in a way such that it follows an exponential growth or decay. And we're going to be using the natural exponential growth and the natural exponential decay because that is pretty much how all things grow and decay, as I just said. So suppose that we have a quantity q, and it's described by an exponential function. So q is equal to a e to the kt. So in this, what we've got is that if we took a derivative, so dq with respect to time, then what this would do is this would give us k lots of a e to the kt, because the k would come down, and this is just the same as k lots of q. Now, what this is known as in maths is a differential equation, because essentially what you've got in this equation is you've got part of the equation, which is a derivative, and another part of the equation, which is a function. And essentially, when those two things are together, this is called a differential equation. Now, it's not super important just yet that you know that this is what a differential equation is. These will come up a lot in year 12. They do pop up every now and then in year 11, but we do spend a topic just on differential equations. Okay, but some of the questions going to pop up in this one are going to reference differential equation. And so I just thought I'd give you the guys a heads up that, you know, if it's got a derivative and a function inside of the equation, then it's a differential equation. So, looking at that, we've got a constant k of proportionality, also known as the growth constant. So this is the constant of proportionality. And you might remember this from direct and inverse proportional. And then that's the same value again down there. So essentially the constant of proportionality pops out when you take the derivative of the exponential. Now the other constant a is the value of q at time 0, and therefore is called the initial value, and it is often also denoted as q0. So when time equals 0. So basically what it's saying is that this thing is essentially going to disappear, turn into 1, because the e to the power of 0 is equal to 1. You're going to be left with that initial time value. So that's what that a value is. Now, as I said, exponential growth is often called natural growth because so many different phenomena in the natural world are described by these equations. So that was talking mostly about growth. Now, decay is just the opposite. So the behavior of our equation, q is equal to a e to the kt, as time increases depends on the sign of k. So basically, this k value up here, so this k value here, is going to determine what happens with our function. Is it going to decay or is it going to grow? So suppose that k is positive, that is that q increases without bound to t's towards negative infinity, and because the derivative is equal to kq, k lots of q, we know that q increases at an increasing rate. This behavior is exponential growth. So essentially, if k is positive, we have exponential growth. Okay, and the converse is just the same. So if k is negative, then q decays to 0 as t approaches infinity. Thus, behavior is called exponential decay. So what I was going to do is we're going to have a little quick look at Desmos and see what those functions actually look like. So here we go. We've got y is equal to e to the, let's just pick a random, or actually we can go kt. Okay, so where time is equal to t. Now what we could do is we could change it. So well, actually for Desmos we have to make t be equal to x. So we get our exponential equation like that. Okay, so what I'll do is I'll increase k, and as you can see, it's an exponential decay. So basically, as it goes up, it increases. So over time, it's going to grow, and it grows at an increasing rate. But as soon as this becomes negative, what essentially happens is we get this decay. So basically, it decreases, and the way that it decreases at a decreasing rate. So the rate is actually going to get slower and slower as we get closer and closer to 0. So it decreases at a decreasing rate. So if the rate of change of some quantity q is proportional to q, then q is described by a simple exponential function. So suppose, conversely, that the rate of change of a quantity q is proportional to q, so that it is that dq dt is equal to kq, where k is a constant proportionality, then q is equal to qoe dkt, where qo is the initial value. So that's basically what I just said here. So essentially, so if the rate of change is some quantity of q is proportional to q, then we can basically rewrite it as dq dt is equal to kq. Okay, that's essentially what it means. So that is proportional to its function q. So it just means that if we have a look at this one again, over on this side, if I take the derivative, so let's say that this is f of x, then g of x is equal to f dash of x. Okay, so if I make this positive, then what it's basically saying is that my derivative is some function or some multiplier of the original function. So it's the exact same shape, except it's just not as strong or weak, or stronger or weaker, depending on what our constant value is. So of course, if it's equal to 1, it's going to give us the same thing. Between 0 and 1, it's a weaker proportion. Again, weaker proportion as we go up, but it's bigger values, and the negative is just the complete opposite. So, yes. Okay, let's have a look at an example of this in action. Boop, boop, boop. Wrong one. Helps if you have the right one ready. Okay, so we've got the current C flowing, and this one is flowing in a conductor, and it dissipates according to the formula dc dt is equal to minus k over c. So essentially, what's happening is there's electricity in a conductor, and it like disappears after a while. So after some time passes, it loses the charge because it's doing work, and this is the equation that tells us how it's losing its charge. Now, each second, it dissipates by 8%. So every second that passes, 8% of the charge is falling off it. And it's falling off the charge that it already has. So, you know, if it has 100% charge, then it loses 8%, which goes to 92. But then if it loses charge from 92%, well, it's not losing exactly 8. It's going to be losing a little bit less, and that decay happens that way. So what we want to do first is we're going to show that V is equal to VO. Lots of, that should be C's, not V's. I don't know why it's come up as V's. But show that V, so it should be C. Oh, there they are. Turns out I just had to do something and it changed it for me. So show that C is equal to CO, e to the negative KT, and it satisfies this differential equation where CO is the initial current of the conductor. So how are we going to solve something like this? Okay, so what we're going to do is we're going to start off by substituting CO, oh sorry, not CO, we're going to substitute C is equal to CO. So remember, this is our initial value of C. So basically before it started, e to the negative kt into the derivative dc dt is equal to minus k on C. Well, minus k of C, I should say. So what would happen is we would get this equation that would look like dc dt is equal to, sorry, let me rephrase this. So what I can do is I can rewrite this as d dt of C is equal to minus k, lots of C. Now remember our C is CO, e to the minus kt. Okay, so this one here is just a little trick I can do to isolate the C by itself, because remember on this side we are differentiating C with respect to t. Okay, so if our C value is CO, so what I can do is I can go, so I've got dt of CO e to the negative kt like this, and that's going to be equal to, so just checking to make sure I was actually recording, and that's going to equal to minus k of CO e to the negative kt. Okay, so let's go with the left-hand side. So the left-hand side is our dt of CO e to the minus kt, okay, which is equal to, Now basically I'm saying take the derivative of this with respect to t, so the minus k is going to come down the front, it's going to leave us with co e to the minus kt, which is equal to that right hand side. So then we've shown it, so there we go. So pretty straightforward, I think, that one. So it's just showing that left hand side, so the derivative was just equal to minus k lots of the function, which is what we said before in that previous bit. Part B says find the value of k in exact form and correct to 4 significant figures. So find the value of k in exact form and correct to 4 significant figures. Okay, so we're going to go to part B now. And part B says, well, let's try at time is equal to 1. Okay, so at t is equal to 1, our value of c is going to become, so it's going to be k, or minus k, lots of, sorry, not minus k. So what we're going to do now, the reason why we did this equation up here, to show that minus kc is basically equal to minus kco of e to the minus kt. So effectively what we're going to do is we're going to say, okay, well our k, so our k in this case is essentially 100%, minus our 8%. Okay, so it's going to give us 0.92. So what that's going to do for us is going to give us the equation c is equal to 0.92 of the original amount. So, okay, that means that 0.92 CO is equal to the initial amount times e to the negative kt. Okay, like this, because we're essentially finding what 8% less of 100% of the conductor is. Okay, so that's where this bit comes from here. So it's, 8% less of 100%, so 0.92 or 92% of the original amount. Okay, so putting that into this equation here, okay, we can take the COs from both sides. That's going to leave us with 0.92 is equal to e to the minus kt. Okay, taking the natural log of both sides, and we get log of 0.92 is equal to log of e minus kt. Okay, and so by doing that, we get log is 0.92 is equal to minus kt, and then the log e is going to cancel out. Okay, now remember we want at time is equal to 1, okay, because this is our first point that we've checked. Okay, so at t is equal to 1, so at t is equal to 1, we get log of 0.92 is equal to minus k, so k is equal to minus log of 0.92, so that means that k is equal to, so k is equal to minus log of 0.92, and that gives us to 4 significant figures 0.08338. So that's our value for k. So our equation for our conductor is CO e to the minus 0.08338 t. So this is our equation that we're going to be using. Part C says find correct to 4 significant figures. The percentage drop in value should be in current over 5 seconds. In current over 5 seconds. Okay, so for this part, what we want to do is we're going to say when, okay, so part C is when t is equal to 5. So when t is equal to 5, so what we can do is we can substitute that into our current. So C is equal to CO e to the 5 or minus 5k. Okay, now we know what our k value is. Okay, and we know what our CO value is. Okay, so our initial value is, so CO is equal to 0.92. Okay, and when that's the case, k is equal to 0.08338, and we can substitute that into this. So C is equal to 0.92 times E to the, just want to actually double check this because I think it might actually need to be 100%, but Yeah, no, not 92. It should be 100 because that's what it's starting at. So it's E, so 100%, or 1 lots of. So it's 1 lot of E to the minus. So I'll just write that over here. So minus 5 times 0.08338. So C is equal to, and we're going to put this into our calculator. So E to the negative 5 times 0.08338. And it's going to give us 0.659. So it means after 5 seconds, this is how much charge it has left. So the conductor has 65.9% left. So it means it has lost 100% minus 65.9%, which is equal to, should be 34.1%. Okay, so that's how much it's lost, the 31.4%. Okay, now the last bit of this question is find correct. Find correct to the nearest 0.1 of a second, how long it will take to dissipate to 10% of the original current. Okay, so now what we're saying is we want to see it get down to 10%. So in other words, we want to know when it's equal to 10% of the original amount. So then we can say that, well, CO is equal to E to the minus KT, which is equal to 0.1 CO of the initial amount. Those initial amounts are going to cancel out, and it's going to leave us with E to the minus KT, which is equal to 0.1. Okay. So what we're going to do now is we're going to substitute K is equal to 0.08338 into this, and this is going to give us E to the minus 0.08338t, which is equal to 0.1. We'll take the natural log of both sides. Which is equal to log of 0.1. Okay, so it's going to give us minus 0.08338t, which is equal to log of 0.1, which means that t is equal to the log of 0.1 over that disgusting number, 0.08338. So the time, correct to 1 decimal place essentially, because we're doing it in seconds. So it's going to be log of 0.1 over negative 0.08338. And that gives us 27.6 seconds. And there we go. So that's it for the first part of the exponential growth and decay. And that's an exponential decay problem, okay, by looking at how something decays in that way. With that being said, we're going to do one more video for this little topic, and then we'll move on to the last part. So I'll talk to you guys in the next one. Ciao.